Welcome to MEI Mechanics. We're on the topic of mechanics basic principles, and this is video 1.4, Newton's laws. So Newton's first law can be stated this way. An object will move with constant velocity, so that's in a straight line at the same speed, same direction, or if it's not moving to start with, it will stay at rest, so long as there is no resultant force acting upon the object. And that works both ways. So if it continues to move in a straight line at constant speed, or if it stays at rest, then that means there's no forces acting on it. Likewise, if there are no forces acting on it, then it will continue to move in at the constant velocity or stay at rest. So that explains why if you are able to remove friction from a situation, so think about something like an air hockey table, that puck will just glide along the table without slowing down. That's what it naturally wants to do if there's no overall force acting on it. So one way of stating that, a more concise way of stating that, is this. So the sum of all the forces equals 0. Now, so that's a situation where you may have a number of different forces acting, and but they're in equilibrium, and that's what we mentioned in some of the previous videos. So if I was to add them all together using vector addition, I'd get a total of 0. And then Newton's second law, well, this is what happens if the forces don't add up to 0. So if there is some overall force on the object, then it will accelerate, so its velocity will change, but that acceleration will be related to that force. It will be in the same direction as the force, and it will be proportional to the size of that force. And the constant of the proportionality is related to the object's mass. So that is the most concise statement of Newton's second law. So the resultant force on an object is equal to the mass times the acceleration. Note that the mass here is a scalar quantity, the acceleration and all the forces are vector quantities. You'll simply see that just written as F equals ma without the summation sign. In that case, the F was standing for the sum of all the individual forces that might be acting. So we can actually put Newton's first and second laws together. In a sense, Newton's first law is included within the second law. So if that sum equals 0, that means the acceleration is 0, and no acceleration means exactly that. It means that it's either staying at rest or it's keeping constant velocity. And then Newton's third law is sort of an odd one out. It's not about the object itself. It's saying that any time that there's a force acting on one object, there's another force acting on another object which is equal and opposite. So if you imagine, if you are, say you're standing on a skateboard and you try to push a trolley forwards, that trolley might move forwards, but you'll also move backwards because if there's a force acting, if you're applying a force to the trolley is also going to apply force to you, which is equal and opposite. You also see this when we're dealing with objects which are connected by a string. So the string is sort of a mediator for this effect, but you'll always have equal and opposite forces acting on the objects which are on either end of the string, because in a sense they are applying force onto each other via the string. So can that help us when we're thinking about force diagrams, or thinking about what might happen in a situation where we've got some objects which are interacting with each other in some way, and where we, in this case, if we know that there is no acceleration, so if this thing is resting, okay, so pay attention to the language here. We've got a ladder which is resting against a wall and resting on the floor. So what that means is that we're expecting the overall acceleration to be 0, or the acceleration to be 0 of this object, which means that the overall force has to be 0. So if we draw our force diagram, think about what forces are acting firstly. So we know that there is going to be a downward force from the weight of the ladder. Because this is a smooth wall, that means that there will be a normal reaction force, but there can't be a frictional force from the wall because we're told that it's smooth. But it's a rough floor, so on the floor there'll be a normal reaction force and there'll be a frictional force. Alright, now what we can say is because these forces, because this thing's at rest, the forces have to add up to 0. That means that the horizontal and the vertical components must add up to 0. So if we look at what's happening in the horizontal direction, that is just saying Newton's first law, Newton 1. In the horizontal direction, we have, if we're calling this one the positive direction, so F is acting in the positive direction, and the other horizontal force is X acting in the negative direction, so we'll add those up by doing F minus X. That has to equal 0, and we can conclude therefore that normal reaction force here, X, must be equal in size to this frictional force F down here. And similarly, in order for the overall vertical force to be 0, that means that R minus mg would equal 0, and therefore R is equal to mg. So they are things which we can get out of this just by applying Newton's law. Now let's think about this situation. So imagine that we've got a ladder which is leaning against a rough wall, but it's on a smooth floor. So we draw a similar diagram to before, but because we've now got a rough wall, we can have friction here. If anything was going to happen, the ladder would be wanting to move downwards, wouldn't it? So the friction would be acting upwards. But here there's a normal reaction force, but because it's a smooth floor now, there can't be any friction. Now the problem is, if we now look at this, there's only one horizontal force acting, this X. So in order for this situation to arise, then X would have to be 0, which is basically not possible. So in other words, it's not possible for to lean a ladder against a rough wall on a smooth floor. It will always slip, and so it will always end up landing on the floor. Okay, so here's a classic example of Newton's law. Newton's law is being applied. So we're given the mass of the car. We're told that's 900 kilograms. We're told there's a driving force of 3,200 newtons. Now remember, the driving force is always acting forwards, and a resistance of 1,400 newtons. And the resistance always acts against the motion of the car. And we want to find the acceleration of the car in that situation. So we have a driving force, 3,200 newtons, acting in that direction, and then a resistance acting against that motion of 1,400 newtons. So if we take this as the positive direction, we know that the overall force would be the 3,200 newtons, which is positive. But because the 1,400 is acting backwards, that's negative, so we're adding minus 1,400 newtons. So that's 1,800 newtons. Now obviously there's also the weight of the car and the normal reaction force, but we know that those are going to balance out anyway, so we don't necessarily need to include them if we're just dealing with horizontal motion. But what we do know, of course, is that this overall force, F, is equal to ma. So if I write down Newton's second law like this, F equals ma, I know that that F is 1,800. I know that the mass is 900, And the thing that I don't know, which I'm trying to work out, is the acceleration. So if I rearrange that, let's say A is 1800 over 900, so that's 2 meters per second squared. Okay, and you can see a neater version of that there. The only difference in this diagram, of course, is that we've represented this just as a particle. We'll get the same conclusion. Okay, here's another situation. So this time we've got a girl who's got a mass of 48 kilograms standing in the lift, which is accelerating upwards at 2 meters per second. So probably worth indicating on here that acceleration 2 meters per second squared. She has a weight of mg, so that will be 48 g acting downwards, and there must be a normal reaction force ultimately from whatever she's standing on, scales perhaps, acting upwards. And that's the thing we're trying to find, so we'll call that R. Okay, so what can we say? Well, again, if we call this the positive direction, up can be positive, then the overall force acting upwards is that R, because that's going upwards, minus 48g. And we know from Newton's second law that that is equal to ma. Okay, so that is equal to 48 again times 2, because we know the acceleration is 2. So this is just another statement of F equals ma. So if I rearrange that, I'll see that R is equal to 48 g plus 48 times 2. Okay, now remember that g is equal to 9.8 meters per second squared. So now it's just a case of putting those numbers in. So 48 times 9.8 plus 48 times 2, and we get a result of 570 newtons. Okay. Now notice where that came from. That came from the weight itself, 48g. So that's what would be that's what the reaction force would be if the lift wasn't accelerating. And we've added another 48 times 2, so we've added something on to that reaction force. So it's a larger reaction force than you'd experience if the lift was stationary. And so on those scales there, she'll actually see her weight increase as the lift accelerates up. And then later, if the lift starts to move at a constant speed, it will go back to normal. And then as the lift decelerates, say she's reaching the floor which is going up to, then she'd actually feel lighter on the scales. Okay, so here's the next part of this question. It's now moving upwards at a steady 15 meters per second. And from our force diagram, just write down the reaction from the floor. Okay, so the point is here, because it's a steady 15 meters per second, that means that she's not accelerating. Okay, If she's not accelerating from Newton's first law, you know that the overall force must be 0. So this 48 G must equal this R. Okay. So we can just write it down. Alright, R will literally just equal 48 G. So we need to multiply. And to 3 significant figures, that is 470 newtons. And then we mentioned earlier as well that if the lift is decelerating, so it's been moving upwards and now it's decelerating, then the effect then is going to be that you will feel lighter. Okay, and that's because well, we can either represent this as an arrow which is still in the positive direction with a negative acceleration on it. So these two forces must add to give an overall negative value. That means that this R must be smaller than the 48G, and that's why she'll feel lighter, and the scales will read a lighter reading as well. So that concludes video 1.4, Newton's laws. The next video will be video 1.5, introducing the Suvat equations.